Good morning, good afternoon, good evening from wherever you are in the world. Thank you for joining today. Today's solution share out, Geomagic solution share out webinar is going to be focused on 3D scanning for aerospace applications, large scale data processing and large scale data handling. Today I'm joined by Kenny Hart, Senior Sales Engineer at one of our US partners, Neometrics. He is going to be presenting a number of different workflows and examples focused on aerospace applications for 3D scanning across hardware and across software. I'm Guy Buttle. I'm the product marketing manager for Geomagic at Octom. I'm going to be hosting today, so you'll see my face at the beginning, you'll see my face at the end, but Kenny's going to take center stage today. A couple of housekeeping bits before we get started. On the GoToWebinar control panel, there is a questions box. If you have any questions throughout the webinar, we're going to save them for the end. We're going to leave about 10 to 15 minutes at the end to answer any questions you've got. So anything that you think of as we run through this presentation, feel free to drop it in there and we will answer them right at the end. Without further ado, then, I will pass over to you, Kenny. Looking forward to it.
All right. Yeah, good morning, everybody. Thank you, Guy, for hosting us on this webinar. I hope everybody's having a good Tuesday. So as Guy mentioned, I'm the Senior Sales Engineer with Neometrics Technologies, and today we're going to talk about some of our 3D solutions for aerospace. Get this going here. All right. So before I kick it off, just a little bit of background about myself. So again, I'm our Senior Sales Engineer. I've been with Neometrics since 2011 as an intern before graduating from University of Central Florida. It puts me about 12 years of experience with 3D scanning, 3D printing, reverse engineering, and inspection workflows. About now, I've got at least 500 live software and hardware demos under my belt in front of prospective customers, and instructed over 600 professional students across varying industries after sale. So on a personal level, hobbies, I'm an outdoor photographer and enthusiast. I love getting outside. I love doing stuff with my family. I've actually done a few feature-length articles and had some photos published in our local Florida Sportsman magazine. So I'm pretty proud of that. To get to Neometrics, this year, 2023, actually marks our 20-year anniversary, which is really exciting for us. We offer a range of 3D scanning and 3D printing solutions, as well as reverse engineering and inspection applications as well. So our industry partners, obviously Octom is one. Again, they're gracious enough to have us on today. Our main 3D scanning line is going to be Creaform. So those are our professional handheld 3D scanners. And then Peel 3D is our entry level. It's actually underneath Creaform. It's our entry level type of scanner. So we'll hit on those a little bit later. To kick it off, our mission here at Neometrics is to partner with our clients by understanding their unique requirements and aiding in developing, deploying, and supporting effective solutions. So we don't sell boxes or anything like that. As you saw, we have access to a very comprehensive suite of 3D scanning and processing tools. So we can custom tailor each individual solution for each individual application. And then we provide ongoing support after the fact. I like to think that kind of signified with our ongoing relationship with our pretty diverse client list. You see here a lot of our bigger aerospace customers, along with automotive, more recognizable boating industry, medical, entertainment, defense, educational. So we've got a huge range of customers, and we enjoy working with all sorts of industry leaders. So today's agenda, we're actually going to be presenting a common 3D scanning aerospace application from start to finish. So we're going to showcase a complete progression from 3D scanning to reverse engineering and then to inspection. We're going to discuss how those apply to the aerospace industry specifically. And then once we're going to follow all that up with a handful of our customer success stories. At the end, we'll, as Guy said, we're going to field some questions. So attendees, if you got anything, please put them in the question box, and we'll be sure to get those answered. So to kick our story off, so let's say we're an aviation MRO service shop. So for those of you who don't know, that's maintenance, repair, overhaul. So these kind of shops get ongoing contracts to inspect, repair, and or replace various items on aircraft at regular service intervals. And we're going to look at a propeller blade today. Very typical, the customer, so the manufacturer is unable to provide the CAD data. That's fairly typical. We see that for any number of reasons. Either they're not allowed to, or it's expensive, and it kind of falls back on the MRO shop to be responsible for providing a way to showcase that they can inspect and they can repair back to manufacturer specifications. So to do this, we're going to use industry-leading tools to streamline this process. For step one, we're going to 3D scan a gold standard part, so one that we know is good. Step two, we're going to take that scan and reverse engineer it into a usable CAD model. And then step three, we're going to inspect a subsequent blade scan against that CAD model. That'll bring us to demonstration one. So for this, again, we won the contract for this ongoing propeller blade service. However, the CAD file isn't available for any one of the reasons that we kind of discussed already. So first, we need to capture that scan data. We're going to do that with our Creaform HandyScan Black Elite. So this is our flagship bread and butter scanner. You'll see it's our handheld model. It's the one that covers 90% of what you would need to do in a 3D scanning application. So I'm going to play this video here, walk you through it. This is me scanning the blade. You can see this is a blue laser scanner, and we've got 11 laser crosses. We're gathering 1.3 million data points a second here. So this is a very, very fast scanner. We can gather data extremely quickly, and we can maneuver around freely on the part because kind of the part looks like it's got some polka dots on it, right? Those are positioning targets. They allow you to scan within motion, as well as you see me flip the part over. I need to get the trailing edge and finish up the scan. That allows me to do that freely and just add data to my mesh. I do want to showcase like the end of my scan. What I don't want to do is be like, here's the scanning, and then ta-da, here's the mesh. Don't pay attention to behind the curtains. So I've finished up my scan, right? You saw me scan one half, scan the other. I've got a few little pieces floating around here. So we got some, the wood brackets that I use to hold it up. Maybe I scan some myself. We can select that scan, and we're scanning direct to mesh. So I can select that mesh, delete those triangles that I don't need, the ones that are floating out in space. And then from that point, this one process button takes our preview scan and turns it into our final mesh. So this is it. That is all the mesh processing you need for this blade. It's just that quick. If you don't know what I'm referring to when I talk about a mesh, I'm going to turn the edges on here, and you can zoom in and see all these little triangles all over the part. So a mesh, STL, OBJ, all these are somewhat interchangeable, at least for this purpose. They're all made up of a bunch of triangles. It's basically a 3D picture that we may need a post-processing software of some sort, which we're going to talk about to take advantage of that information. A little more information on the HandyScan. So we have models that go up to 12 microns or 5/10,000ths of an inch. So you're talking very, very high fidelity, highly accurate data that we can use for metrology circumstances. Each one of those triangle points are accurate to have that single point accuracy. We're also ISO 17025 accredited, which is really exciting and unique. If you're looking at some of one of these for to service as many customers as possible, having that is very important to make sure that you're up to their standards and you can prove out your accuracy and things like that, repeatability and traceability as well. So we've got a self-positioning. I talked about the targets. So the scanner self-positioning, you can see here, I've got these targets on the airplane wing. So we put the targets on the plane wing, and that allows us to lock into the part. So we don't have to worry about vibration or movement, which is awesome, because traditionally when you go to scan, let's say you're doing it in a shop with a lot of other stuff going on, everything else has to cease to be able to do that. And scans are typically, they take a long time. So with this, I can scan while the other teams are also doing their work on the aircraft, and I don't lose any accuracy or anything like that. It really is a game changer when it comes to, time to service. I've got a part on the right, so you see the wheel, not an aircraft part, but just to showcase that we can scan glossy, shiny, chrome, dark surfaces, things that traditionally you would need to, do some sort of surface prep to gather that data. With our scanner lines, we can actually gather that without surface prep. On the bottom, we've got it actually employed in an automated sort of environment. We got it attached to an arm. So if you have parts, repeating parts, doing over and over and over again, we have actually have a number of these on arms being utilized in this sort of sense. So it takes away the human having to drive it. And then our resolution, I kind of hit on, you can see the type of detail we can pull off of parts on that bottom picture. So it's just how small those features are, and we can get it very, very sharp. As far as portability and setup, so we're unmatched in that. We have this all fits down to a suitcase, size thing you could travel anywhere with. It's a plug and play setup. You pull it out, you plug plug your cable in, plug it to the computer, and you're ready to go. And then again, we talked about instant meshes. So scan your part, click that one processing button, takes a few seconds, minute, and you've got your mesh ready to go. So really nice system. All right, so what do we do when we get that scan data? So we got the object, we've scanned it with our scanner, we've got our scan data, our mesh, so we can either go to a model or go to create a model, or we can go to an inspection purpose. We're going to kind of go to the model, and then later you'll see the inspection after that. So for reverse engineering, that's going to bring us to our premier tool. That's going to be Geomagic Design X. So our video demonstration number 2, I'm going to walk through the creation of the CAD model of this blade that we just scanned. So we're going to utilize Design X to generate the CAD, and then we're going to utilize that CAD for our downstream processes. So this is the layout, just real quick before I launch the video. This is the most comprehensive reverse engineering software there is. We combine history-based CAD with 3D scan data processing to get your fastest path from scan to CAD. We got a fully automated tool set. We're going to show you just a dabble in that a little bit here for efficient surface and feature extraction. So to start the video, again, this is very similar, be familiar to anybody working with any of the latest CAD programs. We've got the tools across the top. We've got our parametric tree on the left side there, so we can adjust things as needed, as you normally see. The way I've had this set up is I already have a few features extracted. So I've got one side of the blade done. I'll show you how we do that on the other side. And what we're looking at here is the mesh already broken up into these auto segment regions. So what the software does is it goes through and applies a region. They're not surfaces, but just areas on the mesh that it recognizes as individual features. And then we'll use those to extract the geometry. All the tools in here are based on this mesh sketch that we're going to go through here. So very similar to a sketch where you would choose a sketch plane and then sketch on it. But in this, we've got this 2D cross section that is going to cut through the mesh. We can also pull what we call a silhouette range and get a 3D profile, because we want the full profile of that outer edge of the blade. Okay, so what it's going to do is it's going to grab that and project it to our sketch plane. And it's going to leave us, when I hide the mesh here, you'll see pretty clearly this reference polyline, this pink reference polyline. These are similar in 2D to what the regions are in 3D. It tries to break that up into geometric segments, so arcs, lines, things like that. For these sorts of edges, I like to use splines. So what I'm going to do is actually grab a spline and fit it all the way down that leading edge and then all the way down the trailing edge. And it's going to apply those right on top of that, basically trace it. I can draw a straight line and snap it to the end for the overall height of the blade, and we can constrain that dimension. So everything's fully editable, fully constrainable once we apply this geometry. I'm going to get everything bound up. I want one full profile here. So I need to adjust the length it looks like. I went a little too far in on the end of the blade, so I can definitely delete that dimension or adjust it out. And then I want to get a nice tangent arc in there to make sure that the leading edge wraps up really nicely into the end of the blade. So once I do that, we've got our sketch profile totally done. I can then exit the sketch. And from here, we're talking about standard modeling tools. So we're going to take that extrude and we're going to pull that both directions from that center plane to make sure that we get the entire width of the blade within that, that solid body. And then we'll take our surface that I'll show you how to create here in the next step. And we're going to cut off the piece that we don't need and keep the piece that, encompasses the blade geometry. So once we do that, what's really cool is this deviation tool, the auto accuracy analyzer. So it allows us to analyze any surface, any feature in this software and let us know where we are in or out of our specified tolerance. You saw that little tiny spot towards the root of the blade. That would be something you would tune out using this, thing that we're going to do here next. But for our purposes, that's pretty good. That I'm happy with that. So this loft wizard, this is how I create the size of the blade. This is my favorite tool in the entire software. What this allows us to do is grab a region, right? And then tell it how many segments we want to create a loft across that region. And this is going to automatically do it. So we're going to start at 15. That sounds pretty good. The more complex, the more you need. The less complex, the less you need as far as the profile of that surface. All right, so it's going to take a second and it's going to extract all of those segments down the blade, you can see here. So, and then you can see the underlying surface that's going to be created through all those segments. These are pretty dense. I've got 170 spline points. I'll adjust those. I want those as far down as I need to. I want this as sparse as possible so I can get the smoothest possible surface. And I'm going to turn my accuracy analyzer back on. Inside of the tool, we can see exactly where we're deviating. Okay, so we can decide, say, okay, I've got this high deviation area, and we can freely drag and drop these plane cross sections in these areas of high deviation. Now I moved it over, so it fixed that one spot, but you can see there's things that need to happen in between. So you can actually drag and drop copies of that plane, and it will update that cross section, add all those deviation locations. So we're basically tuning out our deviation, and it's showing us a live result. This is the fastest way that I've found to replicate complex surfaces in a CAD software. So we're gonna, we got the endpoint there. I've got a couple little areas that need to be tuned up. And at that point, we've got a fully green blade profile that looks really good. Okay, there's, again, a little bit left over there. You can fine tune those by playing with the nodes once we get our sketches. But that looks really good. Everything is in place. I'm going to extend that surface out a little bit just so we make sure that we exit that CAD body totally. And then we're just going to, lop that other piece of the CAD off, and that'll leave us with just the geometry of the blade. All right, once I hide that, I'll hide the blade. The leading edge of all these airfoils has a round, so we're going to do a full face fillet, very similar to the same tool that you would utilize in your, familiar CAD program. So all these tools translate over very well. All right, so once we get that nice round in there, we need to create the root of the blade. And so I've already done this, again, a very similar method. I've done the loft on that segment, on that in segment of the root. So you see I'll roll through on here just for time saving. And now I need to connect those two. So I'm going to do one more loft between the root and the blade. And I'm going to make sure those surfaces are tangent so we get this really, really nice, transition through here. So seamless transition, make sure that curvature looks good. If it doesn't quite match up, you can always add a new segment in between. You can draw guide curves on the mesh so we can ensure that we get that entire thing as accurate as possible and as clean as possible. Once we have the blade, the only thing really left is that cylindrical hub or that rotational hub. So this is another really nice tool that we have, rotation or revolution wizard. So again, we have all these wizards. These are our automatic feature extractions. And what we can do with this, very similar to the loft wizard, is we'll grab all the segments of that revolve and then use that to create an automatic loft. You can designate a specific center axis, so you make sure everything is on center. And then here I'm going to go through, I'm going to click every little region on the mesh that would coincide with a cross section down that revolve So it takes a second. There's quite a few of them in there. I've sped this up just a little bit, but I've selected everything. Okay. And then when we go to the next stage, we get this new view that allows us to play with our resolution and our accuracy via these slider bars. So we can get that profile looking really good or very, very close to it. Even if it's not perfect, I'll show you, it's really nice. We can adjust that here in a moment. But once I'm happy with that revolve, I can click the checkbox and make sure that does a revolve merge and merges that into the rest of my body. What's really nice with all these wizard features is you can see over here on the tree, it creates a parametric feature. So not only does it insert the body, but it also makes a sketch that we can fully go in and constrain and adjust along with the revolve. I'm going to pull that corner out just to make sure that that comes to a nice, chamfer there. And then the last tool, we got this fillet tool, and you click on it, you think, oh, that's cool. That's just a fillet tool. But we have this estimate radius for mesh button, which is awesome because it instantly will measure that corner and push it up to the mesh and give us what it thinks is that radius. And then we can fine tune that number from there and make it something when we think about design intent, what it was most likely originally manufactured as. Last step, double check your accuracy analyzer, make sure you're accurate everywhere on your mesh. And then from there, we can export that CAD file as just a basic solid with no history tree. Or what's really exciting is we can go to our favorite CAD package and transfer our tree line by line over to it and have our parametric feature there. So I've launched the SolidWorks one. I got this sped up because it's basically putting all these features in, one after another, transferring between DesignX and SolidWorks. And you can see here, it's building all of our stuff. So we got the surface and the first extrude already done. It's putting in all of these splines for the second surface, and then it will cut that off, basically doing exactly what we just did, rebuilding it all in SolidWorks. All right, so it's creating a hub here at the bottom of that blade. And then once it does that, connects everything, we'll do the last revolve, and that should finish it up. So once I hide all the stuff, it'll be a little more clear what's going on here, but there we go. We've got our CAD model. It's in SolidWorks. It has everything. It's fully featured. It's got a full parametric tree, so we can do design changes after the fact or adjust what we need to, maybe for some specific dimensions. So that is the entire process of taking the scan and creating a parametric CAD file. So for a quick recap on DesignX, we've got our scan, we've got our data set you can see there. And then from that data set, DesignX allows us to efficiently extract sketches and geometry to a parametric model and, check all that with your accuracy analyzer, and then finally send that file to your favorite software. And that'll bring us to our third video, our third example, the final stage in this whole workflow, which is going to be utilizing Control-X, our inspection software. So this brings quality control criteria to an interactive, comprehensive, yet familiar platform for shortened learning curves. You'll see here it's very similar to, again, a CAD program when it comes to setting up your inspection process. Again, I've got my video here. So we got the airfoil CAD file that we just created, already imported, and you see a couple of dimensions already on the end of it there. So I'm gonna launch the video, and Control-X, just like DesignX, is laid out very similar to your favorite CAD program. Got the tools across the top. We have our feature tree over on the left side that groups everything, all of our like tools to branch it, basically branches of those trees. And what I want to do from here, you can build the entire inspection process without a scan. So you can do it all ahead of time before you even produce your first part or check your first part. You can also do it kind of in sequence. So I'm going to bring a scan in first. I guess showing you here the table, the data that doesn't have any results yet because we don't have any scans. So this is what it would look like if you set the whole thing up. You have a blank table. That table is going to be projected to a report later. But here I've imported a new scan. This is a new scan, and you can see there's some funky stuff going on with it, right? It's not aligned, and it's got some damage there. Well, when I import it, I've already put the alignments into my tree. So when I click Run Inspection Process, it aligns the part, and it extracts everything I've already called out to the CAD model. So you can see here in my table now, I've got deviation values. I got measured values of these particular features. If I want to add some more, I've got all this access to GD&T and dimensional analyses that I can apply directly to the CAD model. See here, I'm just clicking on that surface and giving it a surface profile. And that will instantly, now that we have a scan, will instantly give us a result. So you can add those as needed, however many you have in your, let's say your inspection drawing. And then we're going to go to a new tool, this new tool, the airfoil analysis, I should say new on this presentation. This is a dedicated tool for extracting airfoil analyses that you would generally find in an aerospace inspection environment. So we can offset a cross section into the airfoil. And you see here, we got basically this is an overlay of the scan on top of the CAD with the deviation plot, similar to our 3D. I want to exaggerate that a little bit so we see a little more what's going on. If you had a worse one, you'd obviously see more deviation. And what's really nice is, again, this tool, when we go to the next stage, it has dedicated airfoil analyses that you would find in the aerospace industry. So we can check exactly what we want to measure, and it's automatically going to check those deviations in our CAD, in our screen here. So we've got overall length from center to front edge, the BA angle, so the actual pitch angle of the airfoil, and maximum thickness. Again, just a single check on these check boxes will actually go through and analyze that. And so what I'm doing is I'm going to get them all laid out really nice, because this is the view I want projected in my inspection report later. All right, we can adjust tolerances here, so to replicate exactly what you have on your call out sheet. And then once we're all done with that, we click the checkbox, and that goes, applies to our inspection program. Now, you may have 10, 15 of these, or 5, or however many in your actual inspection protocol. You can set them all up ahead of time. That way it measures all this when you do scan your first blade. But that's how quickly you can apply these, these types of things. So in an inspection application, you're generally trying to do this under the clock. I'm going to throw a real quick 3D compare on here. This is a basic 3D compare tool, basically the opposite of our accuracy analyzer in DesignX, just to give us a little idea of what's going on. And you can see, again, those area, this deviation area, we got some damage going on that were clearly shown in that. With this other tool we're going to use is deviation location, and this allows us to inspect damage, corrosion, anything that puts dents in the surface of your part. So we can come in and select the area specifically that we want to analyze. And this tool is going to put like a virtual surface across the airfoil surface and then measure those deviations back to that surface. I've selected I've got some vectors. I got the front of the airfoil and the end, the overall length, that end point is references. So you'll see we'll use those in a second. But in this view, I'm basically telling it to flag anything that has a deviation from the virtual surface of greater than 10 thousandths, and then report anything that has a depth greater than 60 thousandths. So those are going to be the critical dimensions that are deviations that I want to make sure that we get in our report. Okay, so you can see there flag 6 of the 9 as being past that 60 thousandths threshold. And so when we go to the next stage here, I'm going to select the ones. I'm going to do all of them just so we don't get too cluttered. And again, we have dedicated inspection tools for deviation, again, that you would generally find in this sort of environment. So you may want to know maximum depth of each one, along with the relative location of that maximum depth to a couple of reference features. In this case, the leading edge of the airfoil and the end of the airfoil. So we get these X, Y, same as you would put a tape measure on, using past technology or past workflows. So again, I'm going to get that organized, make sure that looks nice, because the shot is going to then be put into the report. So I want to make sure my dimensions all look really good. And once I do this, we'll go over it. But the next part will update, all these dimensions for the next part. So I'm going to show everything. Again, I've got my central hub, I've got my cross section, and I have my deviation. So I have everything here that I want to check this airfoil, and I want to go ahead and throw it to an inspection report. So when I generate a report, I have all my features that I've created over here on this list on the right. And then I can also choose a report format. I've got a specific Geomagic one that I'm really happy with. So I'm going to grab all the features I don't need, right? The initial alignment is kind of superseded by the best fit, the final one. I also have a couple of reference features that I don't really care about putting in the report. So I'm going to grab all those, get them out of there, organize mine in the order that I want, and then make sure that my, pre-written scripted fields that project to my, let's say my first page, information on the project is all going to be put in there. You can see it on page 1. Okay, and as I scroll through, we got images of the CAD file, images of the scan, some alignment statistics, so our best fit alignment. And here's where we got our first kind of analysis. So there's our group 1, our 3D dimensions. You can adjust that view if you need to. We got our dimensions there in the table. And then here's our airfoil profile. We're going to change that. It's a little cluttered. And then the last one obviously is our deviation locations. So that one looks good. But I'm going to come back to this cross section. It's a little convoluted and a little dense on its information. So I just want to have just the dimensions that I care about, not all the little reference features and stuff in there. So what we can do is we can change that, have it just project those dimensions, and then I'm going to get a new shot here and replace that shot. You can see down there in the bottom left, that's the image that's going to go to our report. So I'll bring that report back up, click rebuild. That's all you got to do. Updates all of your stuff. So if you do a new shot for 5 different features, it's gonna update those. You can add in custom shots after the fact. You can do anything you want to in this report. I can export it as a PDF. So you save this file away or send this to your manager, your customer, whoever. And what the beauty of this software is, we can take that process that we just set up there right in front of you, and we can utilize that to basically duplicate a new result and replace that scan with a new scan of your second part, third part, fourth part, fifth part. That's all you have to do to get a new report. It's going to align, extract, update, and spit out a new report for each feature. If you really want hands off, this batch process tool is cool. If you got 50 scans, you can just dump them in a folder, point this at that folder, tell it export PDF or Excel to this folder, and click go. And it's totally hands off. You walk away from your computer and it makes a new feature for each of those, and it runs, let's say, for a couple hours, gets them all finished. At the end of the day, you got a stack of reports. So, with Control X, we've got this really cool ability to set up, put all your time into the initial setup, however long that takes you, however complicated that needs to be or as simple as it needs to be. And then after that, your inspection time basically comes down to the time it takes to scan a part. All right, and just a quick overview, you wrap up Control X. So by capturing, we've got our data there, and then we can apply that to a CAD file and grab the dimensions and grab that color map, and then of course spit it out to a repeatable inspection report. By grabbing 100% or close to it of that surface data, we're gathering way more dimensions, way more information than like what you would typically do with a CMM or hand tools. So we're kind of taking that next step of why our parts are meeting spec or not meeting spec instead of just pass or fail. So just a circumstance comes to mind. I was part of an inspection process where, where we had this big assembly and all the feature components within the assembly were all checked out, all good before assembly. But when you put it all together, they were having fitment issues. They were having to bend things into place. And from scanning the assembly, we could clearly see everywhere that the assembly process was torquing parts and throwing them out of spec. So we were able to determine, hey, we need a little more leniency here, or we need to have more accountability on our tolerance stacking. So it shows you anything you want to see there. With that, that's going to wrap up our process there. So again, scan the part, reverse engineer the part because we don't have the CAD, and then from there we can inspect our components to that CAD file. So really nice. With that conclusion, I'd like to share a handful of our customer success stories. So applications that are very similar, ones that we've actually taken part in. You'll notice they're all going to be reverse engineering. So I don't have any Control X examples here. I tend to find that our aerospace customers like to keep those inspection workflows tight to their chest. I see it as kind of a market advantage. So, those sorts of things, they'll keep under wraps, but these are, the individual reverse engineering applications that we've had that they've been happy to share. So we'll walk you through those now. So for case study one, advanced composite structures. So these guys create helicopter blade adhesive helicopter blade abrasion strips is what I'm looking for. So we're going to reverse engineer those helicopter blades from some scan data here that we take at their facility. These abrasion strips are made to prolong the wear on the blade and space out that maintenance interval that we kind of just discussed further. So it's a really cool application, but again, they need very, very precise data on that leading edge of the blade. So in this instance, we actually use our MetraScan black lead, similar technology to the scanner we looked at earlier, but instead of having a local tracking on the scanner with targets, we got this middle picture here. You can see the tracker over on the left that sees the part and sees the scanner, and then the scanner anywhere within its working volume takes the data. So we can do large areas, large parts with no or very little targeting on the part. You still lock into the part just like the little scanner. Again, just scaling up the type of application. Of course, we use Geomagic Design X to go through a very similar process that we went over with the modeling of the blade to do these airfoils. And you can see that we've got the scan and the CAD on the right. All right, so our advantage, 3D scanning, assured advanced composites. They could create tooling that perfectly matched the complete surface profile from the outset, substantially reducing their design phase. So no more tons of iterative steps to get everything just right. They can model right to the blade that they need. Case study two, reverse engineering a Dassault Falcon 10. So we're taking that step up in magnitude of part size and we're doing an entire aircraft, right? So in this instance, a large aerospace company wished to retrofit an existing Dassault Falcon 10 with new aftermarket equipment. All right, so the problem with that, one, getting a whole getting a whole plain CAD file is very expensive or impossible, to get that from the manufacturer. The other issue we run into, this plane stopped production in 1989. So only a year after I was born, the chances of a really good complete CAD file even being available is very, very small. So we brought in our long range scanner by Faro. It's our focus scanner. With how these work is you set the scanner on a tripod and it shoots the entire room, basically 360 degrees. In order to get all the way around the plane, we put it in different locations around the aircraft, above the aircraft, below the aircraft, and that gave us our full scan. We also went inside to get the cabin as well. You kind of notice the picture of the scan on the last page. So we took all that data and then we actually utilized our MetraScan again for the individual components that need to be reverse engineered for their purposes, and we scan those again with the MetraScan. And then in Design X, we imported the scan of the plane, got it aligned to a coordinate system, and then imported all of our component scans and aligned those to our low resolution complete scan data for the plane. So that way we have high resolution components all throughout space where they need to be. Then we modeled them all in place right where they needed to go. So over on the right, again, we've got our scan data, really nice data set of the plane and of the hatch door. And then you can see the CAD models that I eventually created from those. Case study number 3, our customer DER services. So maybe you're you're doing maintenance on these parts, but you have a part that eventually falls out of tolerance to be able to be repaired, right? So the holes are too walled out, they get bent, any number of reasons why this is deemed unrepairable. So we scanned a good bracket for these guys, a winglet fitting, and they decided that they want to start offering these, replacing them with their own. So we're going to scan the part and then deliver them the model, and they get their approval, do all the testing to be able to start outfitting winglets with their own versus trying to either source ones that don't exist or buy extremely expensive ones or that there aren't really any around. All right, so we scan that. This guy, we scanned it with the HandyScan Black Elite again, and then utilize Design X. So they throw away the old part. We've got the scan of the new part here, the good part, and the replicated CAD file, which was, this is a fairly simple looking part. It's actually kind of complicated because we have these different angles on different faces that need to be correct. The different angles on the through holes need to be correct. And a lot of these spaces that look planar, you can see the regions there, kind of map them out, actually have like subtle curvature and things like that to them. So that's very hard to replicate with hand tools. So we utilize the scan data, created our CAD file, and they were able to jump right into production. Case study number 4. So we're not doing, as far as we looked at some structural stuff, now we're going to look at instrument panels. So Nexair Avionics, they outfit old planes with the latest and greatest navigational and user interface technology. You know, a lot of times they got to replace most of the stuff. They have new panels, new instruments that go inside those panels. But you know, if my truck, if I get a new truck, I still want to keep my cubby hole or, you know, my glove box or whatnot. Same thing with this, right? We've got that glove box up at the top right. Nice storage place, looks like the only storage place in there. So they want to make sure that that transfers over to their newly outfitted instrument panel. So we scan that with the handy scan, again, created an exact replica in 3D CAD with Design X, and that allowed them to replace that. So they actually reported that they took our CAD model, manufactured the first one, and they got a perfect fit on the, you know, first shot. Didn't interfere with anything inside. All the bolt holes matched up, and everything worked perfect. So, and it looks great. So really happy with that. Again, first fit, first iteration, it means faster time to market. And it's a cool offshoot from this is, you know, these are low production parts, so they didn't really want to invest in tooling for mass production. So they're actually taking these and 3D printing the replacements that they outfit the plane with. Lets you use the printer that you have, that you're making all kinds of other parts on, to make these as well. Saves you on floor space and time and all of that, or cost. So very cool application. And then finally, our case study 5. So digitizing a carbon fiber drone blade for CFD and FEA. We had some engineering students with the University of North Dakota contact us. They wanted one of their carbon fiber drone blades reverse engineered, specifically for computational fluid dynamics and finite element analysis. So with this, you know, typically, again, we've kind of hit on CMMs and old methods where we can measure these features. You know, they don't give us complete data of the profile of the blade, and that, you know, the closer you can match to that blade, the closer that their computer models will replicate what's actually going on in real life. So in this case, we 3D scan this, so we have really dense data, not sparse data, able to reverse engineer it, very similar fashion to our blade we did earlier, and give them a CAD model. So more accurate CAD file means better downstream results for activities like computational fluid dynamics, finite element analysis, or 3D printing of duplicates when you eventually need them because they break. Go through here. All right. So that's going to wrap up our case studies. And before I end this, I do want to show, you know, just a real quick overview of our scanners. We've talked about the handy scans. We got a couple lines there. And the MetroScan we touched on, the MetroScan and the Handy Probe, which is actually a handheld CMM. Those all are kind of one big kit that you can have together. The GoScan I haven't touched on yet. So this is our white light handheld color scanner, which is really cool. And it also tracks based off of geometry and texture or color. So you don't necessarily need targets. This is awesome for like freeform surfaces, artwork, stuff like that, that you don't want to put targets on or apply any sort of surface finish to, or if you want the color of that to come through. The Peel 3D, again, our entry-level solution, is basically a baby GoScan, not quite as fast, not quite as big a scanning area, resolution, accuracy, stuff like that, but is a very, very cool feature set especially for the price. It's a nice option. We've talked about Design X and Control X here in our examples, obviously. I also use Geomagic Wrap and Geomagic for SolidWorks quite a bit. So Wrap is a 3D scanning and imaging software. You can scan directly into Wrap. You can import line data in Wrap, and then you can optimize that scan for either extracting features off of it, going to some sort of analysis software, or putting a NURB surface wrap over it. So we get a real nice surface. So this is this is an awesome software for taking a scan of a physical part that's pretty complex surface-wise, putting a NURB surface wrap, like a shrink wrap surface on it, and then getting it able to be interpreted by your CAD file, your CAD program versus trying to deal with importing STLs, which generally doesn't work. Geomagic for SolidWorks is a cool plugin directly into SolidWorks. So it's a subset of the Geomagic Design X tool set put into a plugin in SolidWorks, so you can work parametrically in your SolidWorks interface. For those of you who want to stay within that universe, and do all of your work in there. So another option for you. That's going to conclude my presentation. So definitely want to open up the floor to questions. Guy's gonna field them and read them over to me as they come through. So yeah, we have anything good?
Yeah. Thank you for that. That was super interesting. It's always great to see the breadth of different use cases. Obviously, we've only got 45 minutes, and it would be great to go in depth about each one. But being able to show how the workflow that you put forward translates to parts of different complexities and different sizes is really cool to see.
All right.
We've got a few questions here. As Kenny said, if you've got any as we go through, if any of these questions spark more questions, feel free to add them in the questions panel. The first one here is about time. You obviously mentioned your various different scanners that you guys support, but how long did the process take for that part that you showed us?
So the scan, yeah, so I had it a little sped up, but that whole process is, I look back at the video, it's like 5 minutes. So, I mean, 5 minutes to target the part, 5 minutes to take the scan, and that scan to final mesh, so ready to export and reverse engineer. So extremely fast.
Do you know how long the actual reverse engineering took? Obviously, you showed us a part of that, but it would be interesting to know how long it takes to go from physical part to usable CAD.
Yeah, so that part, I think I spent about an hour or so on that one. It all depends on how complex the part is, how complex the surfacing, whatever you need to do there. If I went in and dimensioned everything, constrained, as anybody working with CAD knows that, that does take an appreciable amount of time. Maybe take an hour, maybe 2 or 3. Definitely the fastest way I know of to reverse engineer and fully constrain an airfoil. And then obviously there's, again, as everybody knows, the last 10% you can get hung up on. So it just depends on a little bit of luck too there. But yeah, you're talking a couple hours and you've got a fully featured CAD model. And then I guess to iterate that to the next step, if you do inspection, again, and something else that's very reliant upon how much you need to inspect. You saw me pretty much set up the whole process that we took, or that we did right there in front of you. If you had, let's say, 10 of those cross sections, again, you multiply that by 10. If you had more deviation or more dimensions, you could add some more in. But yeah, I mean, you're looking at something is quick. If you need a color map and a few dimensions, you can have imported, formatted, and exported report in 15 minutes. If you got a first article inspection where you got a couple hundred dimensions, I mean, they take a number of hours. What I really want to hammer home on the Control X, though, is that once you get that first one done, everything else is just predicated on how long the scan takes, which again, now we're talking minutes, to repeat a measurement on each subsequent part. So it's a very cool workflow.
Yeah, we could definitely spend an entire session looking at the automation of those parts. But it's great to know that you set it up once, and then however long your production run is for your parts, it's just a case of how quickly and how efficient you are with the scanner.
Yep.
We've got a question here that about the reverse engineering in Design X. So when you were reverse engineering that blade face, why did you use the loft wizard as opposed to something like a mesh fit function?
Oh yeah, that's a great question. So you could use either one. So a mesh fit, when we talk about that, you're taking a surface and you're sticking it down on that region. The problem with the mesh fit, you do have some control over it, but once you make it, especially if you're going to another software, it kind of is what it is. So it's not a parametric function. And so if I want the ability to adjust those, if I want my cross sections or whatever to be very specific, Maybe I want that I want that able to be editable later on. So that's the reason why. I also find long, thin things like blade profiles like that. I tend to have a lot more luck very quickly doing a loft wizard versus a mesh fit, just without tweaking too many settings. So, but either one works.
Yeah, I think especially for things like blades, when you are as you showed us, exporting all of that, not only the solid model but all of the construction geometry as well, having everything separately when you come to manufacture something that's that complex is always useful. It's much better to have more information than not enough when it comes to then
Right.
needing to program toolpaths or something like that to rebuild it.
Oh, sure. Yeah. If you make your surface and it's expanded, it's a good point as well. If you're programming two paths, you want that parametric surface behind the CAD model so you can do your whole toolpath across it, off, starting off at the end of the leading edge of the blade and then going off at the end of the trailing edge. So it gives you more information to work with there. So yeah, that's definitely correct.
Great. We have one here. This one is more around the inspection side of things. Do you need a reference CAD for the deviation analysis, or can you use the surrounding area of the mesh to compare it to?
Good. Yeah, great question. So you don't need a CAD file. It's always a little more streamlined, especially to set up when you have a CAD file, but you can certainly bring in a scan and use that as the reference or extract reference features from it. And then, obviously you can measure the part to itself. And then from subsequent features, you can import a new scan with that old one as the reference. And because you've attached reference features to that initial reference one, it'll then pair those with the new scan. So you can definitely utilize it without scan data. If you want, solid rounded dimensions or specific dimensions, a lot of times that CAD file is going to be what you want. But you could certainly measure scans to scans.
Great. We've got one here that is, I guess, asking the question is, can you scan outside? I assume that is there a limit to where you are scanning? I guess that kind of ties it to the scanner that you're using.
So yes, so it depends on the scanner. So the handy scan, I can go scan something out in our parking lot. So that's really nice, and for our automotive customers, for marine customers, a lot of times that's where you're scanning. You may not have a shop to put something in, so you want to do it wherever you can. Other units, so the white light scanners, they tend to wash out with the sunlight. So you either need to bring some sort of canopy or something to give you a good amount of shade, or scan at nighttime. The big system, the Metro Scan, so we just can't have the tracker pointing out in the sunlight. We have customers that utilize it outside, but again, they're utilizing it under a canopy or something where they're not flooding the lenses with sunlight as they come in. But we could definitely make it work outside. Inside, we can do that obviously as well. Production environments, inspection environments, all that, because we can compensate to all those different environments.
Great. This last question we've got, I think, kind of ties on to this. You've obviously made a good impression. Someone is asking how they can get a quote for a project.
Okay, great. Yeah, actually, that'll bring me to my next slide here. So we've got our sales and our services team. If you have a project that you need done, whether inspection, reverse engineering, 3D scanning, 3D printing, all of those inquiries can go to Mandy Howard. She's our account manager, and I'll leave the information up here for you. Sales related questions of equipment, that will go to our sales director, Vic Neesham. And then if you got any technical questions about any of this, feel free to hound me with any questions. You can send me an email or whatnot. I'll get to you on the technical side of things. Yeah, you said that was the last question? We got any more coming in? I'll leave this up.
There's one more coming after that. This one is around fixing broken components. So obviously the part you scanned was looked like it was all there. There wasn't any chunks missing, but this question is asking if there are broken areas or parts that are missing. Are you able to scan and rebuild those when you're reverse engineering?
Gotcha. Yeah. So on my DesignX overview slide, not to everybody remember, but the scan is actually kind of sparse. As long as you have all the data you need to replicate the geometry, let's say on a revolve or a pattern feature or something like that, or even if a surface, if you got relatively most of it and there's like a big gouge in it, when you go to model it, you can just basically ignore that area and utilize the surrounding geometry or geometry in another spot to replicate it. So it's similar application. You only need to scan as much as you need to gather all the information and make sure you can place it correctly. And then on a broken part, again, if you got the two pieces, maybe it's good if you could put them together. But if you're missing it, but that geometry can be extracted somewhere else, then yeah, we have no problem modeling that and replicating. We do that all the time here for service.
Perfect. That looks like all the questions. We've got a couple of minutes left. If anyone has any other burning questions, feel free to drop them in. If not, if you think of anything after the fact, then we'll leave these Kenny and everyone else's contact information up here. Feel free to reach out to them directly. I'm sure they are more than happy to answer any of your questions or schedule a conversation to discuss anything more in a little bit more depth. But other than that, I really appreciate you coming on, Kenny. It was really interesting. It's great to be able to showcase what's possible with this technology, especially for these specific industry applications. Thank you everyone for joining. You'll receive an email tomorrow with the recording of this. So if anyone that isn't on the call today that you think would from this, then feel free to share that with them. This recording will go up on our website in the next week or so as well. So you can access it there as well. But that ends our presentation. Thank you very much, Kenny. I really appreciate the time you put in to showcase this workflow. Thanks everyone for joining, and hopefully we'll see you again on another one of these very soon.
All right, great. Thank you, Guy. Thank you, everybody.
Have a good day.
All right, you too.